Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we look at a research network within the European Cooperation in Science and Technology Association, also known as COST for short, and hear from its Action Chair, María Pilar de Lara-Castells. At present, COST actions bring together more than 50 countries, including new and emerging fields, to offer an inclusive pan-European environment for individuals of all levels of seniority to grow their professional research networks and boost their careers. COST actions are interdisciplinary research networks that brings researchers and innovators together to investigate a topic of their choice for 4 years. COST actions are typically made up of researchers from academia, small and medium-sized enterprises, public institutions, and other relevant organisations or interested parties. The COST Action COSY, that is, Confined Molecular Systems, from a new generation of materials to the stars, aims to provide computational and experimental building blocks for a fundamental understanding and control of confined molecular systems. The platform brings together 45 countries, 32 COST full member countries, and about 260 members. It is structured in 5 strongly correlated working groups, whose objectives range from a first principles description of the interaction between a molecule and its environment, including the interstellar medium, to the synthesis of novel nanomaterials. So, what exactly are confined molecular systems? In short, they are molecules, the smallest building blocks in which matter can be divided, and still retain the composition and chemical properties, but not isolated molecules, and they are constantly interacting with their environment. Conversely, the network focuses on environmental conditions relevant in nanomaterials research with applications, and addresses a rich toolbox of confining environmental conditions, air, liquid, or solid environments, interfaces, as well as effects of strong electromagnetic fields. The main scientific objective of the COSY network is to deliver solid computational and experimental pillars to advance our understanding of confined molecular systems. Why? Because only well-understood systems can themselves be fully controlled. It thus provides a leading research and training school in Europe that is uniquely focused on confined molecular systems and combines new experimental techniques for the synthesis of novel nanomaterials and high-resolution characterization with state-of-the-art first principles, i.e. using just the fundamental quantum mechanical laws of nature modelling, advanced computational tools for molecular motion, modern artificial intelligence, machine learning technologies, and big data science. Moving on to the organisation of COSY, the network is structured in 5 strongly correlated working groups, with the first one titled Intermolecular Interactions, Ab initio-generated force fields and machine learning. This working group is formed by leading experts in accurate descriptions of the intermolecular interaction between a molecule and its confining environment through the development of new first-principle methods and in machine learning representation of intermolecular interactions and applications. Intermolecular interactions determine the physics and chemistry of interfaces, molecular crystals, cells, and even interstellar gas clouds. However, they are not easy to compute from first principles, and while simple models enable us to study large confined molecular systems at long-time scales, they do so at the cost of accuracy and predictive power. Hence, the network develops and applies new computational tools, accurately characterizing intermolecular interactions on small and medium-sized confined molecular systems. The acquired knowledge is next used to define potential models that can be applied to account for intermolecular interaction in large confined structures. The second working group, Molecular Motion in Confined Systems, aims to provide efficient descriptions of molecular motion in large confined structures, including coarse-grained, atomistic, and mesoscale molecular dynamics of metal-organic frameworks and biomolecular environments. The group includes leading experts in 1. Porous adsorbents like metal and covalent organic frameworks with the main purpose of toxic gases capture and separation. 2. Molecular dynamics simulations of confined biomolecules with applications such as the design of bioactive molecules as potential drugs against viruses. 3. Metal clusters in biological environments as acting as non-linear optical contrast agents for tumour biomarker detection. The third working group, confined metal and metal oxide nanoparticles and clusters down to the sub-nanometer scale, is focused on small metal and metal oxide nanoparticles in the size regime below 10 nanometers, where quantum confinement influences the system functionality. A particular focus is on the synthesis and characterization of the stability and novel properties of fluxional subnanometric metal clusters for applications. For example, they can shift the absorption of sunlight of the most popular material for solar energy conversion and photocatalysis, titanium dioxide, from the high energy range, for example from the ultraviolet region towards visible light where the sun emits most of its energy. Therefore, much more energy can be collected from sunlight. This energy is harvested and stored temporarily in the material in the form of charge pairs, electrons and holes, which is a perfect prerequisite for follow-up catalysis. However, the theory developed for metal nanoparticles and bulk materials does not apply for the smallest metal clusters, so that their properties are not yet well understood. In the quest of filling up such a gap, the network includes leaders in Europe in fields such as synthesis of atomic metal clusters in gas phase and solution, transmission electron microscopy, state-of-the-art density functional theory-based modelling, and the highest level of ab initio theory and molecular motion. The fourth working group is helium nanodroplets science and engineering. This group deals with helium nanodroplets as ultra-low temperature, chemically inert nanoreactors for aggregating, cooling, and probing molecular complexes, metallic clusters, and exotic nanoparticles. The structure and dynamics of both the embedded aggregates and of the quantum fluid helium nanodroplets are experimentally probed by high-resolution spectroscopy, imaging, and surface deposition within this group. Moreover, helium nanodroplets impacting a surface allows the realization of soft landing deposition. The droplets dissipate the collision energy of embedded species when impacting a substrate, which are thus deposited with minimal structure changes. Theoretical tools used by the network combine quantum theory with semi-classical and classical methods for the motion of helium atoms, including multi-component metal and metal oxide clusters, nanoparticles, and single atoms, for example. Finally, the fifth working group, Confined Systems in Astrochemistry, focuses broadly on astrochemistry. Observations both from the interstellar medium and laboratory experiments form the basis for the computational and theoretical chemistry and physics methods. The experimental methods at our disposal play an important role, for example, in attractive kinetics and spectroscopy experiments in the laboratory, often mimicking at least partly the conditions in the interstellar medium. Fascinating quantum chemistry and classical physics computational tools have to cope with the gas systems of isolated molecules with high precision and the complexity of the surface and condensed phase systems. Astronomical complex organic molecules, potential building blocks for life as we know it on Earth, are special target systems within this group. As María Pilar de Lara-Castells, the Action Chair of the consortium, explains, the network is a unique combination of experts in chemistry, physics, biology, materials engineering, and astronomy, which makes it intrinsically multidisciplinary. She adds, through 5 strongly correlated working groups, we try to deliver fundamental understanding of everything on the interaction between a molecule and its environment, including the interstellar medium, as well as new materials down to the sub-nanometer scale, bearing interesting applications, such as in theranostics, a method that combines the therapeutic and diagnostic uses of radiopharmaceuticals, that employs molecules to safely introduce radioactive substances into the human body, solar energy conversion, catalysis, and photocatalysis. Besides scientific objectives, the network targets the problem of research limitations in less research-intensive countries, helping young researchers to promote their careers and underrepresented genders to highlight their careers. On the one hand, the network has created the COSY group with the aim of identifying the obstacles women face during their scientific careers and propose solutions to overcome them. On the other hand, the COSY Read My Proposal group highlights that while some countries may face specific challenges, there are initiatives at the European level to support researchers from less research-intensive countries. The first meeting of the group concentrated on grant proposals and manuscripts writing for early and mid-career researchers from these countries. In summary, the COSY COST Action aims to further push understandings of confined molecular systems relevant in new materials and biomaterials research and astrochemistry, far beyond the present knowledge, using the most advanced computational tools and experimental techniques. The working network, COSY, is primarily inclusive, helping underrepresented groups and enabling participants to work freely and independently, regardless of age, gender, or institution location. Action Chair María Pilar de Lara-Castells encourages those interested in the COST Action COSY to reach out via pilar.delara.castells@csic.es. That's all for this episode. Thanks for listening. Links to more information about COST and the COST Action COSY can be found in the show notes for this episode. And as always, stay subscribed to ResearchPod for more of the latest science. See you again soon.